Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
My name is Abby Sellen. I work in a group called Computer Mediated Living, which is a group that specializes in human-computer interaction, which is essentially about understanding the relationship between people and technology and trying to invent new experiences for people on the back of that. So sometimes we draw on technological innovation, sometimes we draw on user understanding, and other times we draw on design. So I'm hoping that through the course of this talk, I can demonstrate through the research that I'll be describing how all of those three disciplines come into play. So I'm going to be talking about new ways of exploring computer input paradigms. And there's no doubt that new kinds of ways of interacting with computers can be revolutionary. It can revolutionize not just the way we interact with devices, but the kinds of devices that we build, and indeed the kinds of tasks that we carry out in our everyday lives. Yet outside of the research world, it's interesting that it's really only in the past few years that mass market devices have made the big leap beyond keyboard and mouse. So with the introduction of the iPhone, we now started to see multi-touch come into a lot of different devices. And hot on the heels of this, we're seeing now the transforming impact of in-air gesture. And Microsoft's Kinect gaming technology was instrumental here. And these changes, in turn, are creating a kind of new enthusiasm for alternative ways of interacting with computers. So we see not just the impact of gesture and multi-touch, but also renewed enthusiasm around things like voice, eye gaze, and even brain-computer interaction, for example. Much of this is down to the maturing of the technology itself, but also the breakthroughs are undoubtedly about design as well. But the point here I want to make is that I think we're perched on the edge of many more radical changes as a result of new input paradigms, which is one of the reasons why I'm excited about this area of work. So in this talk, I want to explore the design problem, really, of how you open up the input space to new possibilities. And I'm going to start by briefly describing our approach to this and also discussing some of the arguments and visions behind why we'd want to do this in the first place. And then I'm going to consider how we effectively design these systems by describing two lines of research, which we've been attempting to do this. In the first line of research, I'm going to be talking about some work we've done in surgical settings. I'm trying to add both gesture and speech to surgical interaction. And then I'm going to talk about how we have been playing around with adding gesture to desktop interaction around a desktop PC. And I'm going to be describing these adventures that we've been embarked on, some of which have involved testing in the wild, which is in itself a challenging thing, which I'll also talk about. And then I'm going to conclude talking about some of the challenges and the lessons that we've learned from trying to do this. Right, so in the title I use the word hybrid, and I use that word deliberately because it says something about the approach that we're taking. So I'm using the word hybrid by analogy to a hybrid car, where you have a new form of power sitting alongside the existing engine within the context of a highly evolved and complex system. So my concern here is to see whether or not we can add new input capabilities which complement what already exists and work alongside ingrained and already successful interaction techniques. So that's what I mean by hybrid. And this is different from a lot of the research that's gone on around alternative input modalities. So a lot of that work looks to replace one input channel with another. And that makes a lot of sense, for example, if you're talking about people with disabilities. So you might use voice to do text input, or you might use eye gaze to take over the cursor control. And it also makes a lot of sense if you're looking at certain situations where, for example, your hands are busy. So if you're driving, hands-free input makes a lot of sense. But we're asking some different questions here, actually. We're asking whether we can enrich new kinds of input without creating entirely new systems. And we're also asking whether we can add new capabilities to existing systems without getting rid of the good bits, without getting rid of the bits that are kind of highly evolved and useful. So why might we want to take this approach? Well, one reason is clearly about offering people choice, right? So when you offer people up choice, they can choose how they interact depending on their circumstances. And this is recognizing that different input modalities have different affordances, right? So if I want to write a paper, I'm going to sit down at my keyboard and do that because a keyboard's great for high input, high velocity input. If I want to sit back on the couch and look through the web, I might grab a touch tablet and do that instead. It's much more suited for that kind of activity. So we can think much more deeply about how we offer up choice in systems. And this isn't just about input, obviously. So if you look at Microsoft Surface, one of the things that's happening there is to try and play around with the physical form factor of that device to allow you have a detachable touchscreen and so on. But other arguments really hark back to much older visions that have been around a long time. So one of the arguments has been that we have these rich capacities for action, and yet we don't utilize the bandwidth of human beings, right? So we force everybody to interact through these little keyboard and mouse input devices, and we're not using everything else. So it's a kind of a bandwidth argument, and multi-touch is starting to draw on that, to let us use 2 hands, multiple fingers, and so on. And another argument goes back to, actually this time way back, so I'm talking about early 80s when people like Dick Bolt started to build systems like Put That There at MIT. And his argument was that why don't we draw on the way that people naturally interact with each other? So looking at interaction more as a kind of dialogue. And I'll just play you a little snippet of it. It's very dated now. It's kind of interesting.
Welcome to the Pavilion. I'm waiting for you.
Pay attention.
Go ahead.
Create a red oil tanker.
Where?
There. Put a blue cruise ship.
Where?
East of the Bahamas. Make a yellow sailboat.
Where?
North of that.
Okay, so you see what's happening there. They're trying to make the dialogue take advantage of the fact that people point and speak a lot. And so it's trying to build much more intelligence into the interface. And the argument is that this is something that we do intuitively, so why don't we build systems that respond in this way? But there's some big issues here, which is how do you add new input capabilities without adding complexity and extra workload for the user? And that turns out to be a really big challenge. So I'm now going to talk about 2 programs of research to give you sort of examples of how we're working through these issues. And I'm going to talk about first the surgery work. Right, so surgery is an interesting domain within which to work, because if you think about why we might want additional forms of input, there are certain situations where it really makes sense to try and replace mouse and keyboard interaction with other kinds of input. So certain surgical kinds of settings like interventional radiology, like vascular surgery and neurosurgery are more and more highly dependent on images, rich data to look inside the body so that you don't have to open the body right up. So with more minimally invasive surgery, there's more dependence on data to see inside. Now the problem is, of course, that if you want to flip through those images, if you want to manipulate them, rotate them, and so on, this is usually done through mouse and keyboard, and surgeons are scrubbed up. They can't touch any of that stuff. So they have to ask somebody to help them with that. And that turns out to be very cumbersome and very effortful. And so we're really interested in how people in these situations get around those problems. So what you see, sometimes people do things in a very unorthodox way. On the left-hand side, you see a radiologist who's essentially what he's done is stuck his hand inside his gown, which is not sterile on the inside, but sterile on the outside. And he's using his mouse. Right. The infection control people really frown on this, by the way, but they all do it. Or more commonly, what you see like in vascular surgery and neurosurgery is that they'll ask an assistant to flip to the next image. No, twist a little bit right. Go up, go down. No, that's the wrong image. Go to the next image. That sort of thing. It can be very cumbersome. So to see how we might address this, we spent a couple of years actually following a whole cycle of development where we aim to put the clinicians at the very center of this design process to see how we can design effective systems for them. And so the way we typically do our work is we would start with some field work, actually trying to figure out how it is that the people are doing the work. What are the complexities of that work? How do they do it in teams and so on? And to look for opportunities where we might be able to put touchless systems into these situations. And it turns out that as we were doing this work in all these different settings, it was the vascular surgeons who were the keenest to get on and build something. And this was a team of surgeons down in Guy's and St Thomas's Hospital in London. And so with them, we started to sit around the table, talk about what they might need. Then we built a series of prototypes, which we tested first in the lab here and brought the team up here to look at. Then we took it down to their operating theaters. We put them in their operating theaters without the patients there to try out how it worked in that setting. And lighting conditions and things are all very different down there. And then we started to use it in real cases. So it's been used in several, lots of new real cases since last year. And so let me just, I'll show you a video. That's the best way to describe in detail what we did.
In minimally invasive vascular surgery, surgeons are reliant on medical imaging to guide them in inserting stents into the aorta and its major branches. Yet currently, because they are scrubbed, they rely on other people in the surgical theater to manipulate the data for them. The Connect for Windows technology presents some real opportunities to allow for touchless interaction. Through close collaboration with vascular surgeons at Guy's and St. Thomas's hospitals, we have developed a system for manipulating 3D images. The system supports the surgeons to pan, zoom, rotate, lock, mark, and fade the 3D overlay to view the underlying 2D fluoroscopic image.
Keycode place mark. Keycode exposition.
We have used voice control for the execution of discrete commands and gesture for the commands that lie upon a continuum and lend themselves to a physical manipulation metaphor. Seamless transitions between gestural commands allow the surgeon to have his attention on the images during manipulation. One of the interaction design challenges we faced was the need for a gesture set to be performed at the bedside in close proximity to other personnel. Therefore, the gestures needed to be confined to the area in front of the physician's torso, as the space above, below, or to the sides of that area may not be sterile. We achieve this through a clutch mechanism whereby the hands can be brought back towards the body to be repositioned without moving the image.
This Connect system has allowed me really to get control of that imaging myself during, of course, the operation. You know, to interact with it as I want, without interrupting the flow of the operation, and without me having to engage my brain and try and communicate to a third party.
Since May 2012, the system has been in use in patient cases in the vascular surgery theater at St. Thomas's Hospital.
Okay, so that gives you a good sense of the kinds of things that we did. Now, as you might imagine, and some things were mentioned here, a lot of design challenges to building these kinds of systems. So we're taking Connect, which, don't forget, is designed for whole body gaming, right? And we're taking it into a situation where you can only see people's torsos. People are tightly packed together. The sterile area is here. So the gesture set had to be much more kind of contained, which put a lot of constraints on how we can actually do things. Another issue is that we had this idea of modes, which I think was briefly mentioned in the video. So what you don't want is any gestures to start making the data fly around. And of course, when teams are talking to each other, they're gesturing. So we had a control mode where gestures had an impact on the system and moved stuff around. And we had a pointing mode, which was the default mode, where whatever gestures took place in that zone didn't have an impact on the data. So having said all that, the process that we went through was fairly successful. So we found that the surgeon's ability to control these images had an effect in many different ways. So for example, one thing we found was that surgeons, so the rotate command was one-handed. We found that they could hold the catheter inside the patient's body and do some of this rotation, which is what they need to do a lot in the course of an operation. Other times you'd see the surgeon standing there fading the 3D rendering on top of the X-ray in and out to get a real sense of where instruments were in the body. So long times of reflection where he would just stand there and do that. And at other times he would talk to his colleague, right? So another consultant would come in about a case, and they'd spend time just fiddling back and forth to see if they get a sense of what was going on. Now, all of these things would not have been possible in that way had they been having asked somebody, a colleague, the whole time, move it to the left, move it to the right, now fiddle it, you know. So it's just hard to express these things, and they really appreciated the ability to be more kind of hands-on without being hands-on, if you see what I mean. But we also found that over the course of deploying these in real cases, we had to revisit a lot of our initial design assumptions. And I don't really have time to go into detail on that, but let me mention two that I think are quite important here. So the first thing is that when we first designed the system, we required the surgeons to wave, as you do in a Kinect game, to get in and out of a mode. And the surgeons didn't like that. They said it was way too inefficient. Is there another way we can do this? And originally we hadn't thought about putting voice in because we didn't want to overcomplicate things. So this is the thing about when you add new modalities, you have to worry about the complexity of the interface. They said, no, we want voice, we want voice. So we put that in. We brought in all kinds of different consultants with all kinds of different accents, and it worked really well. So we then started putting voice in for more of the discrete commands. So every time they had to lock the screen or switch modes, anything discrete, voice worked a real treat, and that was something that we hadn't expected. But anytime they had to do something spatial, that's when gestures came in, and that's when they worked really, really well. So that was one of the learnings that we made, that sometimes adding new modes of input doesn't necessarily make things more complex. Sometimes it makes it easier if you choose the right modality for the job at hand. A second thing that we learned was about the importance of feedback. So we worked hard on providing feedback in the system, big icons that you see the locked icon at the bottom of the screen, just to tell the users what state the system was in. But it turned out that this little feedback window in the bottom left-hand corner of the screen, this is in a large version, was actually the most important bit of feedback. And what this is showing is how the Kinect is parsing the people in the field of view. So what Kinect does is it segments out different skeletons. It tracks the bodies of the different people in the field of view, and it imposes a skeleton model on top of that. And what you find is that when people are closely packed in the field of view, sometimes the system makes mistakes. So in this case here, what you see is the surgeon, the Kinect actually thinks the arm of the surgeon is the arm of the person behind the surgeon. So it's kind of, the skeleton is kind of bleeding into the other person. And what we found is that this was really useful for them to figure out why the system sometimes was messing up. It also meant that they can kind of duck out of the way. So you saw the team kind of ducking out of the way of the zone of interaction. So that was really, really important. So since that time, we've been building and testing a different system, this time for use in neurosurgery at Addenbrooke's Hospital here in Cambridge. And I'm not going to say too much about this system at the moment, mainly due to time, but also because this is an ongoing project at the moment. Except to say that many of the issues are very similar in that they're heavily dependent on image data. In this case, they're more hindered because the images are stuck to the wall. They're not even next to the patient operating table, so they have to get up and go over and look at them. And the nature of the work is, but other than that, the nature of the work is very, very different. So usually they're sitting down, and the surgeon's looking through an endoscope, which is a camera inserted into the body, working on aneurysms operating on the brain and the spinal cord. So it's very delicate work that takes long periods of time where you're actually sitting and looking through in this way. So some of the design requirements for this obviously have been quite different. So originally the surgeon we were working with saw the vascular system and he said, I really like the idea of that gesture, but he said, I've got to use it one-handed because I'm sitting down and I can only turn my body and do this. And we said, okay, fine. We started building it all around one-handed gesture. And then we started to deploy it. And in the second case that he had, things started to go wrong. It's a highly stressful kind of surgery. And he started shouting at the machine. He wanted it to do things without him having to gesture. And afterwards he said, you know, it'd be really nice if I could just shout for it to rotate or shout for it to clip. And it would start doing that for me. And so we're looking at more and more giving more automatic control to the system when he wants it. And so the requirements, as I say, are quite different. So let me just wrap up this little piece of the talk and just say what I think the main learnings are about designing hybrid input in surgical settings. So the first thing is it's kind of tricky. It's kind of tricky to do it right, and even the best guesses can turn out to be wrong when you put these things into practice. But the top takeaways, I would say, is that adding new modalities such as speech and gesture can make interaction simpler and more efficient if you do it right. Another is that whenever you add a new form of input, you have to provide effective feedback for telling users what the interaction zone is, what things are possible, and what the system has interpreted about what's going on in front of that system. And finally, as the neurosurgery shows that there might be a balance that needs to be struck between automatic control and user control, and that these issues are something that designers and developers need to think about pretty deeply. Okay, so let me just move on quickly to the second line of work here, which is moving now from the world of surgery to the world of desktop work. And this is related to a demo we've got outside, which I'll point you to afterwards. But here what we're interested in doing is adding new input capabilities to mouse and keyboard interaction. So this is called the 2-foot PC project, and you might ask, well, why? So we actually started with a technology-focused question here, which was that if you could put a depth camera on top of a computer, let's say your desktop computer, and you could open up the space of interaction around screen, keyboard, and mouse, what kinds of things would that enable people to do? Okay, so it's kind of like opening up a bubble of interaction in the proximate space around keyboard and mouse. And we didn't want to just open this up for the sake of seeing what the technology could do. What we wanted to do was to take a very principled approach to this. And so one of the things we had at our disposal was a whole bunch of work that some of us and our larger community have been working on for years, which is looking at how people do document work. How do they use digital documents and physical documents? What do they do when they're doing their work at their computer? So we really wanted to kind of draw on that and put together a set of design principles which would guide us to design gestures in this space which we hoped would be useful for people, and not just for the sake of doing it. So the design principles we started with were these. And the first one is what I've already talked about, which is in line with the idea of hybrid input. So here what we want to do is to very much to complement keyboard and mouse use and not replace it. You may have seen some demos from other companies, people doing input in the gesture space. And you'll notice a lot of it is trying to replace mouse and keyboard use. We're not doing that, okay? We're doing something quite different here. So what we're trying to do is come up with a gesture set that allows people to interweave mouse and keyboard use with the gestures. So always coming back to mouse and keyboard use and then interjecting the gestures in between. And hopefully we can do this in a way that doesn't add more complexity, but gives more users more power and flexibility. That's the goal, okay? And that's the first big principle. Another big concern was that the gestures would be ergonomic. And what this says is, you don't want gestures where you're holding your hands out here for a long time, right? You don't want Tom Cruise in Minority Report doing this. Because it's tiring. I mean, well, maybe not for Tom Cruise, actually. But for normal people, it would be. So we wanted to make them ergonomic. And we also wanted to leverage the power of gestures. So I talked earlier about choosing the right modality for the right task, right? So what keyboard and mouse is really good at is precise things, right? Precision selecting and pointing. So why would you want to do that in the air? Air gestures are not good at precise pointing and selecting. You've got to hold your hand up for a long time, and it's just not ideal. But what gestures are good at is very expressive things. You can do things casually, you can do them expressively. And that's what gesture's good at. So let's play to the strengths of the input modality. And another design goal really related to this is to try and exploit the power of two hands. So when you have gestures, obviously you've got two hands. Can we bring in gestures so that, for example, you can leave one hand on the mouse as you do something with your other hand? And finally, we wanted a gesture set, and this is a very common thing for making things usable. You want the gesture set to be easy to learn and easy to remember over the long term. So that's what we started with. And then we went on to do something which our designer on our team did, which is to put together a series of animated sketches of interaction. So what I'm going to show you here is an animation. It's not real, but this is often how he will sketch out a design experience so that we can get a sense of it by just looking at what it might look like. So I'm going to start with this one in which we're playing around with this issue of trying to unload what often happens on the mouse hand onto the second hand to try and make navigation easier. And he's done it here in Excel. So this is smoke and mirrors. This isn't real. So what we're thinking about here is an interaction zone that might be next to your keyboard. And this is where you use your non-dominant hand. Your non-dominant hand is very good at doing coarse-grained navigation. Big, large movements, while your right hand, so your dominant hand, does the pointing and selecting with the mouse. So here he's showing moving around a spreadsheet and using his right hand to point and select. And anybody who's got RSI might appreciate this, that you unload some of the work onto your second hand. Another thing we played around with was the idea of quick formatting commands. So here he's doing just a quick freeze of the left-hand pane in Excel and then unfreezing it. So it's playing around with the idea that you might have just quick gestures to do some of the things that you might want to do frequently. In this second animation, we're going to show now the idea now in Microsoft Word of thinking of the hands as kind of proxies for objects or documents. Okay, so imagine these things do interesting things for you as for example, bookmarking. So in this example, we have a document. He's holding his hand up, navigating somewhere else, and when he lets go, it springs back to where he was. So it's the idea of looking at what people would do with physical documents. Here, he's taking a quick glance at an outline view of his document. So just tipping your hand up might allow you to look at something else as you're typing and put it away again. Now note that's a nice spring back action. It's a temporary thing. Or bring in a different document from the side. Right? This is just playing around with concepts here. So you might look at it, put it away again. And it's all one smooth movement. There he's pinning it. So he's bringing it in, he's pinning it, and then unpinning it and putting it away. Okay, so these are they're not precise actions. They're very flexible. They're very casual. Here he's tiling two things side by side. Okay. So quick window layout is another thing that gestures might do, and then untiling them. And here he's going to resize. Flick of the hand. Yeah? So, note, again, none of these things are precise things. None of them require you to hold your hand up for a long period of time. Or at least if they do, we'll get rid of them. Okay. So those were the aspirations. Those are the things we're trying to build. Actually building these systems is difficult. It's a difficult challenge. We've got two of our crack developer team here in the room today who have been trying to build the system. And they're going to show you the demo of it later. And I'm going to show you a video now of what we actually got, which isn't perfect, but we're getting there. And the system that I'm going to show you now doesn't do the on-desk navigation stuff yet. We're still working on that. It concentrates more on the in-air stuff. So let me show you where we are.
We present a system for bringing freehand gestural interaction to the desktop. Requiring only a depth camera mounted above the PC, the system detects a variety of in-air gestures within the proximal space around keyboard and screen. The aim is to explore how such gestural interaction might enhance rather than replace mouse and keyboard use, recognizing that different input modalities have different kinds of affordances. Our main gesture set is designed to be low physical effort, so it avoids sustained in-air gestures and is designed to be interwoven with mouse and keyboard use. It is also designed to be easy to learn by using the keyboard as a frame of reference where in-air gestures happen in the space above the keyboard. The peek gesture allows a temporary glance at another application without shifting focus from the main task. Switching the active window is a two-handed action. If the user wants to keep the selected application open, they pin it with the other hand, helping them to switch tasks to the new window. A pinch gesture invokes search. Note how the hands can move between typing and gesturing seamlessly. Other in-air gestures allow quick ways of doing window layout. For example, a two-handed gesture provides a quick way of laying out two windows side by side. Repeating the gesture resets the state. Some of the in-air gestures use the metaphor of physically grabbing the active window. Then windows can be docked left or right. They can also be minimized and maximized. Finally, some gestures allow quick navigation such as forward and back. There is also a gesture to show the start screen and then go back to the desktop.
Our system is general in its approach to sensing hand gestures and touch. The Connect camera captures raw depth data of interactions occurring on the desk. An adaptive foreground segmentation allows us to isolate the hands. We then use a random forest space classifier to identify salient features of the hand as well as detect the hand pose. Each pixel in the foreground image is classified as either fingertips, shown in pink, the wrist, shown in grey, or the overall hand state, which transitions between different colours as the user performs different gestures. The different hand poses that we can currently classify are shown in sequence, with synthetically generated training data shown inset. This allows us to classify a variety of hand states without requiring full hand tracking. To determine a specific hand pose from this labeled data, we first compute a histogram for each hand across all hand states and select the state with the highest frequency. Using this approach, we can create a gesture recognizer easily by just observing the presence of a specific hand state for a certain number of frames. More complex gestures can also be developed by observing transitions between multiple hand states. We deal with clutter such as books and documents on everyday desktops by adapting our background segmentation model over time and integrating new data that remains static only. This avoids integrating hands that are interacting and moving with the scene into our background model, as shown.
Okay, so a bit of the technology there too at the end. So it's a challenging system to build for many different reasons. But we got to the point where we tested it in the lab iteratively, and then we decided we were going to test it in real life, and by that I mean at people's desks for an extended period of time in this lab to do real work, which is a challenge, right? And we had 6 people using it over the summer for a couple of weeks. And what we were really interested here was to find out what kind of gestures were they finding valuable and for what reasons. Did they ever take the place of doing particular kinds of shortcuts? Because some of the things could be done with shortcut keys. And whether they could interweave the gestures with their mouse and keyboard use, which after all was one of the goals that we had. Another goal was to understand the challenge of using this in a real environment. So were the gestures tiring over long periods of time, something we were hoping to avoid? Were they robust and reliable, or did they become just annoying and distracting? So these are things that we were really keen to find out. Also whether they were easy to learn and remember over 2 weeks. Because it's fine to do these things in a short-term test in the lab, but if you ask people to do them for a lot longer, then the learning is more kind of realistically assessed. So the findings, we've got some kind of early results from the field trial, and it turns out that testing this at a real person's desk for doing real work throws up all kinds of challenges that we just never see in a lab setting, which tends to be nice and clean and very controlled. So for example, one thing is we found that people bring very large objects like documents, coffee cups, all kinds of stuff across the keyboard in the field of view, and this has the potential to trigger things that you don't want to happen. So Pete and Chris, who are building the system, would come in, they'd find a way around it, they'd rejig the code so that it would deal with these kinds of things. Another thing we found was people had lots of idiosyncratic gestures. So we had one guy who would always sit and think like this, and every time he did this, he would close an application, which was not good. So, and then other people would kind of sit like I do this. When I'm thinking, I sit like that, and I'm triggering search. You know, so there are things, you're not going to get that in a lab situation. You're only going to get it when you look at what people really do. And these are very ingrained habits too. You can't ask somebody to stop doing this if that's what they do all the time. So again, we had to change the code design around this, and sometimes think about changing the gesture set as well. So one of the ironies then is that when you try and design a gesture set that interweaves with real interaction, you're more likely to kind of come up with a gesture set that's more easily confused with what people do. So that's a real design challenge to try and get around that. Secondly, so some of the gestures actually did prove to be really, really valuable for people. They love the peek one because that's, after all, something that you can't easily do with a bunch of shortcut keys or mouse interaction. And that was nice for doing things like peeking at an IM window if you're working on something. They also really like the window manipulation docking, especially people who didn't do that with shortcut keys. And just moving from clearing the desktop and moving into Windows 8 and so on, those were really popular as well. And so you might ask, well, if you can do these with shortcut keys, why would you bother? It turns out that having the choice was something people really liked. And so there were some times when, just depending on what tasks they were doing, it was actually easier to do the gesture. And then other times they were in a kind of lean back mode, so they might be not kind of up close over the keyboard and like looking at the web, but they might be leaning back and they just wanted to do forward and back gestures in a kind of more relaxed mode. So yes, they do compete with our ingrained habits, and sometimes those things are more efficient, but just having the choice there and allowing people to do new things was something they really liked. And then finally, while the gesture set was initially easy to learn, we didn't learn enough from the surgery work to put enough feedback in the system. So what we found was that over time, people needed more feedback just to know how the system was seeing their gestures and what it thought was going on. So we added this little feedback bar on the top right, which would just highlight whatever gesture the system thought was being triggered. And that helped people to diagnose when things didn't go as they expected, but it also kind of reinforced their learning over time. So that was a really important thing to do. So all in all, it seems like we've had some glimmers of success for trying to extend the input capabilities around a system that lets, you know, that some people have spent many years ingraining their existing work practices around keyboard and mouse. So actually it's a very high bar to come in and try and change it, or to interweave and try and incorporate new things into those work practices. But we still have a lot to learn here. We have a lot to learn about how users do these activities, how we can design them for them, and what the technical issues are. But luckily, when you have a multidisciplinary team, that's one way in which you can start to attack these challenges. So I'm going to finish up now, and I want to finish up by summarizing with 6 challenges, which I believe are the kind of main challenges for designing these kind of hybrid systems. So the first challenge is to find combinations of input that are stronger and simpler when they're together, rather than more complex and more cumbersome. And I hope I've shown in this talk that you can do that not just by looking at kind of the user research in the area, but from design exercises, from first-hand observation of what people do, and then from evaluation of systems in real-world situations. A second is that part and parcel of this is understanding and leveraging the power of different input modes. So, for example, why use in-air gestures for fine-grained pointing when we have other input devices that do that better? And why use gesture for mode switching when a simple voice command will do that a better job for you? So it's perhaps too obvious to say, but different input modes have different affordances, and they're not simple substitutes one for the other. Thirdly, we have to recognize that achieving this also means achieving a balance sometimes between user control and system control. And this is something that I showed in the surgery work. Well, there's some situations in which user control is crucial, like being able to fiddle around with that 3D model while you're talking to somebody. And other times, automatic control is much more desirable. Fourth, everyday skills and habits can be exploited in the design of hybrid input systems, like designing gestures based on physical manipulation skills, like we had in the surgery case, for example. But at the same time, existing habits will shape how your system is used, and it may give you problems that you didn't anticipate by competing with ingrained habits and competing with the way that people have their workspaces laid out, as we showed in the 2-foot PC system. But again, I think you're never going to know this until you deploy a system in real working practice. And fifth, that adding new input capabilities to an existing system will never be totally seamless or instantly natural. Okay, so users need the interface to help them understand whether they're being sensed in the first place, what the zone of interaction is, what actions are possible, and what the system thinks is going on. Users need all that feedback, and good feedback is crucial to designing these well. And number 6 is testing in the wild. So I'd argue that meeting any of the above 5 challenges means you have to deploy a system for real. And that's perhaps the biggest challenge of all, because you need something fairly robust and reliable to do that. You need an excellent technical team and people who understand users and designers. So we have a long way to go in terms of creating new forms of input and changing current practice. It really sets a high bar for success. But I hope to have convinced you in this talk that it is possible to create these new input paradigms. And when we do, we have the potential to offer users a lot more power and flexibility in the ways that they engage with their digital world. So I'll leave it there. Thank you.
Any questions at all at this point? Oh, hands going up, shooting up.
Abby, where are you on eye tracking?
Oh, good question. We did an interesting internship. We had 2 really excellent interns over the summer looking at eye tracking and looking at where it makes sense to put gaze into systems. It turns out there's a whole lot of literature, you probably know this, on eye gaze and where it makes sense and where it doesn't make sense. So for example, eye gaze doesn't make sense for moving pointers around, but it does make sense in setting the context for other kinds of things. We've been playing around with a technique called the magic technique, which has been out there for a number of years, which moves your cursor to the kind of vicinity of where you want to interact, and then your mouse does the fine-grained work. We've also been playing around with the use of eye gaze plus gesture and eye gaze plus voice. And written a paper on that, which I'm not sure, well, we'll find out in November whether it's going to be published. But we, again, have been testing these techniques with people at their desks. And one of the things you find is that, unlike the lab situation, calibration is a huge issue, right? Because people are up and down from the desk all the time. And if you haven't got the calibration right, everything else doesn't work properly. And there's a bunch of other issues, too. So I think it's a really interesting area. But again, we need to attack this in a very principled way and not just randomly because we do it, because we can do it.
Abby, have you been back to any of the 2-foot PC guinea? Ask them if they now remember any of the gestures that they learned during that 2 weeks.
No, because most of them were interns and they've gone. But we could. However, well, there were a couple of people here still. Actually, a couple of them did say that when the system was shut down, they kind of naturally tried using these things and then realized, oh, so it switched off. So that tells us that some of them start to become incorporated into them, which is really interesting. But as for remembering the whole set, no, people didn't remember the whole set because the ones they didn't use just dropped out.
I suppose the other challenge is that some of the gestures are culturally rude. Or in certain countries. So internationalizing the solution may present a challenge.
Yes, no, that's right.
Just a very quick question here. Regarding those gestures, have you designed a virtual keyboard on the monitor so you can just simply remote control, like pointing to A, and A come out, just completely remove the keyboard?
No, because that would go completely against the design principles. That's about precision, and we don't want to do precision in the air, right? So we've got a keyboard. We don't need one in the air. And the physical keyboard is much better.
Sorry. I mean, was there any measurable improvement in the outcome of the patients undergoing vascular surgery?
It's really hard to measure things like that. So they didn't die. That's good. None of them have died. No, more seriously, it is, and the NHS asks these kinds of questions, and it's, you know, it's a serious question in the sense that to put these new technologies in, often what people want is numbers. But it's, what would you measure? I mean, would you measure the time of the operation? Because it might be that actually giving surgeons this ability makes them spend longer, but they might have a deeper understanding of what's going on. You know, so just getting quantification is difficult, and it's something we thought about, and we sort of given up on how to really do that. What we have is testimonials from the doctors who are using it. And the other thing that's interesting here is that this team is the team that gets the really difficult cases, because they put that 3D rendering system together with showing the aorta, and that's really crucial for doing difficult cases where you can't actually figure out where you're. I mean, it didn't give you a lot of background on this, but usually when vascular cases come in, they don't have that 3D model. They just have the 2D fluoroscopic image, but these guys have the 3D as well, and that helps them do things that other teams wouldn't touch. So they have the difficult cases anyway, and some of them are hugely long. So again, it's hard to kind of quantify. Yeah.
Okay. I think hand at the back was the next one. I think one or two more questions.
In terms of the 2-foot PC, have you any thoughts of how you apply it to, say, the mobile laptop user who may be perching up and working anywhere?
Yeah. So what you'll see out in the demo room is a big rig stuck over the PC, and it looks really cumbersome and clunky. You think, oh, I'd never want that on my desk. But actually, there's no reason why we can't do a much more lightweight, portable version of this that might even be embedded in your laptop. So there are mobile ways to do this. But of course, we're not there yet. We're thinking, we're still refining the gesture set, and we're not we're not at the point where we're doing that. But there's no reason why these things couldn't be made more mobile. So we are thinking about that, yeah.
Okay. I have two questions. So one is, have you ever tried with interaction to go beyond just one PC, like the user trying to upload something to the cloud or to move to another PC, and what would be the reaction? So this is one question. The second one is on learning strategies. Like, do you deploy all of these gestures at once, or have you tried to do the users of deploying just one gesture at a time and then teaching them as they go?
So the first question, transferring things across PC or up to the cloud. We don't have gestures for that at the moment. We do have a gesture, which I didn't show, for flicking a window from one monitor to the other, which is palm down. Now, one of the reasons we didn't show that is sometimes a problem, because when you reach for your mouse, you fling a window. I mean, it's really hard to design these gesture sets so that they interweave and they don't trigger when you don't want them to. So we haven't done gestures for transferring across computer, because of course now we would look at going to the cloud, and I'm not sure you need something physical for that, but it's something to think about. Learning, well, so what we did when we trained people, we just had a visual cheat sheet with all the gestures and what they did, and we ran them through all of them. And I suppose we could have introduced them more stepwise, but we just didn't do that. We said, okay, here's the set, and we'd come around every day and see what they were using and what they weren't using, and ask them why. And so we were there pestering them all the time. And we didn't do a kind of controlled assessment of the learning.
Okay, one more. Anybody? One more question? I think yourself down the front here next. That was it.
I thought the two scenarios were fascinating, and I wondered if they led you to think about different aspects of resilience in the application, because I'm thinking about consistency of response time, even application failure, because in the desktop scenario that may be irritating, but it's not going to cause a real big problem. In the theatre scenario, you get into the boundary of safety critical systems, and you thought about different resilience models. Yeah,
I mean, we obviously worried about that too, but we made sure that in the surgery system there was always a backup. So if the Connect camera failed or the system dropped out, they just go back to the way they normally did it. So we had a guy sitting behind who could take control of the images if it needed to be. So there was never a problem with that. In fact, we were really worried about ethical approval and getting into hospitals and things, but because it was seen as not on the central path, but as a kind of nice to have add-on, it wasn't a problem, and they let us in, which was great. Scary, but great. Yeah.
Okay, we'll probably have to call that time then. Thanks, Abigail. Thanks again.
Yeah, thanks.